All right, my friends, good morning. Next week there are two important things happening. The first is the premiere of the third season of The Mandalorian. Yeah. The second is an exam, starting February 28th, ending March 1st. It's in the testing center. Same thing, basically, to expect in terms of logistics as last time. A late fee kicks in on March 1st at 2 p.m., so try to get in before then. Don't pay money to take tests. Many of you are asking how much of chapters 7 and 8 are we going to get to. I suppose that will depend on how effective you are at asking questions today that derail us from covering new content. You already got one, huh? Can I explain in depth why the Mandalorian? No, but my mind was blown the other day when one of my grad students pointed out that the armorer's helmet has spikes on it, and maybe that's like the Death Watch people that worked with Maul. Maybe she comes from that. Ooh, I don't know. Anyway, some of you are wanting to know what's on the test. Everything is on the test. Chapter 4, which we didn't cover on the first exam, will definitely be on this exam. So 4, 5, 6. How much of 7 and 8? We are right in the middle of 7 and 8. We will probably finish most of it by Monday. So I would say try to be ready for all of it. I would rather tell you to expect that and then have it not turn out that way than to tell you, oh no, it'll be fine, and then not. Anyway, I realize that may or may not be that clear. It'll depend on where we get to today and Monday. But plan ahead to be done with that 7 and 8 study guide by Monday or Tuesday. Now, we didn't meet last time because of the snow, so I posted a lecture online. Hopefully you've seen that. Online lectures are great because you can listen to me at 1.5 speed and get through the same amount of material in less time, so good for you. We talked about competition between SN2 and E2 reactions, and we said that competition depends on the identity of the nucleophile / base and on the identity and characteristics of the alkyl halide. We said that SN2 is fastest for primary alkyl halides, not observable for tertiary alkyl halides, moderate in speed for secondary. We said that the elimination reaction is slowest for primary alkyl halides, moderate for secondary, fastest for tertiary. And so you have this sort of trade-off, and the area where we want to be careful and compare and be prepared for a competition between substitution and elimination, SN2 and E2, is for secondary alkyl halides. We went through this last time. The reasoning process here is you have a good nucleophile that's not a good base. Its pKa of its conjugate acid is around 9. So it's a good nucleophile but not a good base. That means we're not going to do E2, but SN2 would be favored if possible. It is indeed possible and fast for the primary alkyl halide, so you get the substitution product. No need to draw any elimination products. Similarly, with this example, you have a secondary alkyl halide. For those, you want to be worried about both SN2 and E2, but because of the identity of the nucleophile, which is not a good base, but is a good nucleophile, SN2 is going to be what happens. You show that you understand that by showing inversion of configuration at the stereocenter where the leaving group was. Now, if you use a good nucleophile that is also a good base, you need to be worried about SN2 and E2, depending on the structure of the alkyl halide. Secondary alkyl halide, both SN2 and E2 are possible. So look at the nucleophile as both a good nucleophile and a good base. So you've got to draw both substitution and elimination products. Substitution, you show inversion of configuration to get this product. Then elimination, you have to look for beta protons that can be anti to the leaving group. So as an example here, that consideration doesn't matter too much here because each of the beta carbons has 2 protons on it, and but the one that gets removed is the one that is anti or can be anti to the leaving group. In a 5-membered ring, because the ring conformations are not that well defined for a 5-membered ring, you can assume that a proton that is trans to a leaving group can indeed get anti to the leaving group. So this would be the product if we eliminated the purple proton A. This is the product if we eliminated the blue proton A. They're similarly substituted in terms of alkene stability, so it would be difficult to predict whether one would dominate over the other, and I wouldn't expect you to. But I would expect you to recognize all of them as products of the reaction. This gets to the fun questions that we ask where I say, which of the following is or are products of the reaction? Select all that apply. You guys hate those, but that's sort of what you're looking at for these kinds of questions. Right, so let's see. One example that we talked about, and there's only a very few molecules that are good bases that are not also good nucleophiles. One of them is tert butoxide. The reason is sterics. It's too big to attack carbon. Can't get in there to the sigma star, though it can attack hydrogens. So it can attack the LUMO on the beta proton. This is only going to do E2. And of course, E2 is possible for primary, secondary, and tertiary, though it's slow for primary. But if you're using something that's not a good nucleophile, that's the only thing you can do. In any case, we start with this secondary alkyl halide. We're not worried about SN2 because of the identity of our nucleophile or base. So we're just going to show the elimination product, but we got to be careful here because we only have one beta proton, and the stereochemistry of the product, the alkene product, is going to be determined by how that proton can get anti to the leaving group. What I mean is, in this current conformation, the proton is on the same side of the molecule as the leaving group, but you can rotate around the bond between alpha and purple beta carbons such that the proton is now anti to the leaving group. If you want, we can draw a Newman projection with the proton with purple beta carbon in the front. Hydrogen would be, if we're looking from this perspective down the bond, hydrogen would be here. The benzene ring or phenyl group would be here in the back. Iodide is here. Let's see, phenyl group would be here and hydrogen would be there. Okay, the leaving group is anti to the beta proton. So this is the reactive conformation when a base removes that proton and we make a new double bond. Notice that the two phenyl groups are on the same side of the molecule. As that double bond forms, it's like those alpha and beta carbons get squished down and rehybridized to sp2, trigonal planar. So there's no chance for rotation around the bond so that the phenyl groups could change their locations as that double bond is forming. So we exclusively get the Z stereoisomer here and not the E stereoisomer. The identity of the product is fixed by the stereochemistry of the starting material, right? Now, if I had no phenyl group there, if I just had two beta protons, then I'm going to get both stereoisomers, because if I remove one, well, we can go through an example like that, but just imagine there was no phenyl group here, then it would be easy for me to rotate around this bond such that this proton would now be anti to the leaving group, and that would change the stereochemical relationship between phenyl group in the back and methyl in the front. Yes?
If the phenols were E to each other, would it remain E?
Yes, if the phenols were trans to each other, would it remain trans? Absolutely. And so that was sort of what I asked you to do. I said, think about how you would, And this is another great way to probe your understanding of mechanisms and reactions. Which of the following starting materials leads exclusively to this product? All right. So how do you do this? Well, I suppose you could look down the bond between alpha and beta carbons in the product, noting that the phenyl group in the front is opposite to the phenyl group in the back. And then you could imagine saying, okay, in the front, I'm going to put maybe a hydrogen here, and then I need the leaving group there. Okay. So then what this tells me is that my starting material, if it has the iodide up here and I want to get the trans isomer, proton has to be down and methyl group has to be up. Do you see how that's different from what we did up here? Stereochemistry is different at this beta carbon. Questions about that thought process? Practice it, because if you're not confident, you're going to miss it, and I'm getting the sense that you're not that confident, but you're too scared to ask because you don't want me to dump more on you, right? Right, you want to hear it one more time? Okay, to get the E isomer instead of the Z isomer, we need to choose stereochemistry in our starting material such that when the beta proton is anti to the leaving group, the phenyl groups are opposite each other. So I'll draw the Newman projection here. Again, let's see, phenyl, methyl, hydrogen, oops. All right, up here with our first stereoisomer, when those groups, when the beta proton was anti to the leaving group, the two phenols were on the same side of the molecule, right? However, for this starting material, we've changed that situation. When the beta proton and the leaving group are anti to each other, the phenyl groups are on opposite sides. And so as a base removes this proton and we form the double bond and the, oh, whoops, holy Toledo, Batman, that's terrible chemistry. Try that again. Remove the beta proton, make a double bond, the leaving group leaves. Those carbons flatten out. And phenyl, which was anti to phenyl in the back, which was anti to phenyl in the front, stays that way in our product. All right. Sorry, was that clear as mud? What questions do you have? Yeah.
So, if I understand correctly, what you're saying is, in order to get the configuration that we want, we have to make sure the beta proton that's going to leave is anti the molecule to the leaving group.
Yes. Yes, the beta proton that you remove has to be anti to the leaving group. So I see another hand. Yeah.
So when those leaving group leaves, does that molecule just freeze where it is right now and create that double bond in that configuration?
Yes. Yeah, as the leaving group leaves, does the molecule sort of freeze in this orientation as the double bond forms? Yeah, because remember, it's a single step reaction. The transition state involves breaking of this bond at the same time as we're breaking this bond at the same time as we're making the pi bond. So yeah, if groups that are opposite each other in that reactive conformation have to be opposite each other in the alkene product. Yeah.
Would the position of the Newman projection have anything to do with the rate of the reaction? Like with the original molecule, you have the phenyl groups kind of gauche to each other.
Yes.
And then on this one, the phenyl groups are
Oh, that's
one be
interesting.
faster than the other?
Yeah, that's an interesting question. The question is if the reactive conformation that puts the beta proton anti to the leaving group has some steric problems, does that mean that, for example, here where the phenols are gauche to each other, is the reaction slower? Is it harder to get to this conformation than in the other molecule where the phenols are anti to each other? That seems like a reasonable hypothesis. I don't know. You just do the experiment and check. Yeah. Now, yes.
How much if there's multiple leaving groups, like multiple possible leaving groups? Then
Whoa.
we just assume that they're all going to be.
What if there's multiple possible leaving groups? I can't think of a situation that I would give you like that at this stage. We will encounter one like that in chapter something or other, 10, in which we'll have two bromides adjacent to each other, and there will be a double elimination kind of reaction that we'll do there, but we won't worry about that yet. Yeah?
When you're trying to decide if a molecule is a good nucleophile, do you just look at the steric hindrance of that molecule, or do you look at the steric hindrance of the RX?
Yeah, so when deciding whether a nucleophile is a good base versus a good nucleophile, two considerations: pKa, the conjugate acid, and then sterics, and it's the size of the nucleophile. So, for example, tert butoxide has a conjugate acid with a pKa of 19. You would think it would be both a good base and a good nucleophile, but because of sterics, it's not a good nucleophile. But for others, pKa's basically get you what you want to know. Yeah.
Follow up to that. How do you know the sterics of it versus the pKa of it?
How do you know when to worry about sterics versus pKa? Well, because there's only like 3 things on our list of molecules that are not great nucleophiles but are still good bases. The Smith text talks about tert butoxide and then talks about these other ones, which I used to draw, but inevitably we just abbreviate them with their 3-letter abbreviation, and then we forget what the structure is. But basically, these are all sterically hindered bases. Yeah?
I think you might mention your study guide that Broken Island is a good nucleophile, but its conjugate base has less than 0.
Right. So the study guide does mention that sort of an exception to all of what we've talked about is that you can actually use the halides as nucleophiles, even though their conjugate acids are really acidic. We're not worrying about that in this chapter because the halides are the leaving group. We're not doing any examples where the halides are nucleophiles. We'll talk about why that is. There are basically a couple of different ways to be a good nucleophile. One's to have really high energy electrons. The other is to be large and polarizable, but we're not worrying about halide nucleophilicity right now. Yeah?
So when we're determining the versus 4 bases, are there conjugate acid associated?
Yeah, so will you have a pKa table on the exam that'll have conjugate acids of the common nucleophiles that we're dealing with? Yes. Except, of course, for the alcohols and water and alkoxides and hydroxide, yeah. Uh-huh.
So what about the sterics of the alkoxide makes it a poor nucleophile?
What about it makes it a poor nucleophile? Let's see, I can draw, this is not tert butoxide, and I can't actually draw tert butoxide. Delete. The best I can do in Spartan is tert butanol, but just look at, imagine that the proton on the red oxygen isn't there, so this is imagine the conjugate base of tert butanol. Basically, for that oxygen to be a good nucleophile, it needs to approach another carbon very closely, but used to be a laser pointer here. There's a flashlight. This oxygen can't approach a nucleophile very closely because, remember, it approaches from the backside. There are groups pointing in this direction. They're going to bump into the phenyl groups. Where am I looking? Yeah, they're going to bump into the phenyl. Yeah, sorry, they're going to bump into the methyl groups the closer you go. Did I miss somebody over here? Yeah.
Would you ever have to do a chair flip to get the hydrogen anti to the leaving group in the hexane?
Excellent question. Thank you for asking. I was wanting to talk about that. Would you ever have to do a chair flip to get things anti to each other? So, yes, and will that always be possible? Mostly, but not always. So, let me, of course, show you some examples. If you have a ring like this where, I'm just trying to make stuff up on the fly. Notice that of our beta protons that are available, this one is on the same side of the molecule as our leaving group. Therefore, it is not reactive. Whereas this blue beta proton is trans to the leaving group. And so the question is, can that beta proton be anti to the leaving group? So to answer that question, what we'll do is we'll draw a chair. I'm not going to go through how to do this in any level of, I'm not going to go through how to draw the chair. So we've decided that this proton in the back is not ever going to be anti to the leaving group because they're cis. And in a ring, you can't change cis-trans relationships. That's fixed by the fact that it's a ring. So what we're looking for are protons that are trans to the leaving group. This one here is indeed trans to the leaving group, but it's not currently, relative to the ring, but it's not currently anti. In fact, they're gauche to each other. So the real question is, if you do a chair flip, and if that chair flip is reasonable and possible at room temperature or whenever you're doing the reaction, can that proton be anti to the leaving group? So if we did the chair flip, the bromo goes axial. One of the beta protons goes axial. Now it's anti to the leaving group. And now you can do the elimination reaction. And the product that you would get would be this one. All right? Yeah?
If you had like a double cyclohexane ring, is it possible to chair flip that configuration?
Can you chair flip a double cyclohexane ring? Yeah, yes and no. Do you like that answer? Related question, or yeah, go ahead.
So, how would you know?
I'm gonna actually tell you the answer. Don't worry. Okay, go ahead.
How would you know which carbon the bromine electrons are going to still bond with after this? Does it matter? Like you have it coming down, but if it, I don't know, would it go?
So, what alternative are you thinking about? This way? There's no leaving group over there, so you can't go that way.
Oh, you're right.
We're forming a pi bond, leaving group leaves. Yep. All right. So I'm going to answer the question about double cyclohexane rings, but for now, if it's possible for the chair to flip and that allows a proton to be anti to the leaving group, that's just fine, and you're going to draw the products from that. Even if this conformation is higher in energy than the other, because of Le Chatelier's principle, even if there's not very much of this at equilibrium, once it forms, it reacts, and that perturbs the equilibrium and pulls material to the right-hand side of the equation. Now, I believe the question about double cyclohexane rings was about this kind of system, which is called decalin, because there are 10 carbons in it. And there are two kinds of decalins. There is cis decalin where the two groups here are on the same side of the ring and the first ring, and then there is transdecalan where they're on opposite sides of the ring. I want to choose the other one. Yeah, okay. All right, so how does that affect the shape of the molecule? We'll call this ring A and ring B. We'll draw the chair for ring A first, and then for ring B, for the cis-decalan, I have the two ring substituents there. One is axial up, the other is equatorial up. And so I have to then, this is a CH2 group and this is a CH2 group, and I have to connect them with the rest of the ring. It can be done. I'm not going to ask you to draw it, but since organic chemists don't get to flex that often, we'll just do that. And then if you turn it sideways, that's a chair. This cis-decalan actually can chair flip, all right? Again, you asked, and we're talking about it briefly. It's not the most important thing, but it will provide context for an example that I'm going to give. My wife often tells me that my jokes require far too much setup, and I think that's true for examples in OChem too. All right, so we do the chair flip. Up carbon 1 becomes down carbon 1. Down carbon 2 becomes up carbon 2. So the ring substituent on carbon 2 needs to be up axial. It used to be up equatorial. The one on carbon 1 needs to be up equatorial, used to be up axial. And then we're sort of looking at it. We can't really draw a chair for that first one because we're sort of looking at it dead on. But the point is that as long as these two groups are cis to each other, both chair conformations are possible because it's easy to connect these two carbons that are cis to each other with a bridge of two carbons. If you wanted to look at this molecule in a slightly different way, if you don't like what we drew there, we can call this 1, 2, and 1. All right. So it turns out that cis-decalans readily flip. If you want to see this, we can make a model, or I can, I'm going to just see whether Spartan actually has this or not. No. Fine. Dun, 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 dun. All right, well, this is what the cis-decalan looks like. Notice that this is the axial up group, this is the equatorial up group, and they're easily connected by a 2-carbon bridge. All right, so that's part 1 of the setup, meaning if you were doing some elimination chemistry, both chairs would be accessible to you, and so if you have a proton that's trans to the leaving group in one of these two chairs, it's going to be anti, and you can do the elimination reaction. Now, the transdecalan looks like this, just 2 chairs side by side. And this is the only viable conformation for the transdecalan. And the reason for that is simply that imagine trying to do the ring flip and try to connect the down axial substituent on carbon 1 with the up axial substituent on carbon 2. There's not a 2-carbon chain that'll span that distance. And if you try to go ahead and try to make a model, and you'll break some pieces because you can't actually span that distance. Because of that, we're going to say that transdecalins are locked in that conformation. So, I have asked a question before somewhat related to this. Hold on. Oops. Trying to remember how to set it up. Yes. That's fun. Which are the elimination product or products from this reaction? And the tempting thing here is that relative to that leaving group, I have 3 beta carbons, right? Got this one in purple, this one in, oh, whoops, that is not a beta carbon. This one, which we'll highlight in blue, and then I guess we'll use orange for the methyl group here. And it looks like this bromo group is down, so maybe if one of these hydrogens are up, can those actually be anti to the leaving group? And if we don't draw the chair form of this molecule, we're going to miss an important detail. I think this might be a problem on your practice exam. If it's not, I'm remembering it from the exam. So maybe hope you've seen it before, I don't know. If we try to draw this molecule in its chair conformation, what we would see is the 2 beta protons that are in the ring that are trans to the leaving group. Oops, here's a leaving group in gray, blue beta proton. Those are locked in an equatorial position. They are trans to the leaving group, but they cannot get anti to the leaving group because that chair can't flip. So, yeah.
Just, can we talk about briefly conceptually why it's so important that it is anti to it? Like, why can't it just take it from there?
Right. Why is it important that it be anti? The answer is the reason the beta proton is acidic to begin with is because of sigma to sigma star hyperconjugation, whereby a carbon hydrogen bond that is anti to the leaving group lines up with the sigma star. Yeah. Yep. So that's the origin of that anti requirement. Right. So, of our available protons, are there any that can be anti to the leaving group? Do you see any that can be anti to? Go ahead.
Sorry, can you just briefly cover why it can't flip?
Why can't it flip? So,
Is it similar to the last example where it was a train?
yes, that's exactly right. This is a 2-carbon chain is simply not big enough to connect, not large enough to connect across that large of a gap.
And in our example, the one we're trying to connect with is the bromo, or the, oh no, I see the 2.
No, so we've added some details to this molecule, some methyl groups here and there, but the core structure is a transdecalin and the leaving group's in one of those rings. So this ring conformation is locked as is, and all of the groups on the ring, axial versus equatorial, actually stay where they are. So that's why blue and purple protons, even though they're trans to the bromide, can't be anti to the bromide. Do you see anything else that could be anti to the bromide? Go ahead.
So if we look down the carbon-carbon to the methyl group next to the bromide,
Sure.
we can swing those three hydrogens.
Yep. If you, so, oh, right. So aren't you glad you're having that moment here instead of after the test? Right. Because we can rotate around this carbon-carbon bond, one of these protons on the methyl group can get anti to the leaving group. So that's going to be the reactive proton. And so our product from this reaction should be exclusively this one. And not the other options, which are tempting because they would lead to more substituted products. But you can't get there because the leaving group can't get anti to the purple and the blue beta protons. Okay, so now you want to know a decision tree to know when you have to worry about this. And there isn't one. What you should do is rely on your knowledge of orbitals as the explanation for why a group has to be anti to the leaving group in order to be reactive in an elimination reaction. And then you use your knowledge of conformations and of chairs to figure out whether that's possible. As I said, this is the one example I can think of where a locked chair would prevent protons that are trans to the leaving group from being anti to the leaving group. Yeah?
Based on like the original drawing, not the chair drawings, how can you tell which groups are axial or equatorial? Like what if you assume that those hydrogens are
Right, so what if you started with the other chair here? That's a great question, and if you did, let's call this again carbon 1 and 2. Let's say I put 1 here and 2 here. On carbon 1, the methyl group would then be equatorial with my ring substituent down. On carbon 2, the methyl group would be equatorial with my ring substituent up. Immediately I would see I got a problem there because I can't connect those two with a 6-membered ring. Now, you may have to make a model to convince yourself that that's the case, because some of you are like, the heck I can't, ta-da. But it doesn't work that way. If you make the model, seriously try it, you'll be twisting and popping bonds open because you can't span that distance. I'm trying to think of a good 3-dimensional illustration of this, and I really can't. You're probably going to have to make a model. Or I suppose maybe someone's done this before. You could Google attempted chair flip for transdecalan and see if somebody's animated it, and you'd see it going and not making it. So there we go. Probably not with those sound effects. All right. So we now need to try to integrate all of what we've talked about, substitution and elimination reactions, with what we're learning about reaction mechanisms and our other mechanistic hypothesis where the leaving group just leaves. And I talked about this in the lecture that was posted. But I want to introduce a new way of looking at reactions. We've done reaction coordinate energy diagrams like this before, where this axis was energy and then this axis was some measure of reaction progress. That could be the distance between the alpha carbon and the nucleophile, or it could be the distance between the alpha carbon and the leaving group, some measure of how the reaction's going. But notice that in the SN2 reaction and in the, well, at least in the E2 reaction, there's two different things that are changing, right? We're changing the carbon-hydrogen distance as we remove that proton, and we're changing the carbon-leaving group distance as we remove that leaving group. So, and similarly in the SN2 reaction, we are at the same time as we're breaking the carbon-leaving group bond, we're making a new carbon nucleophile bond. So we're going to try to make a three-dimensional reaction coordinate energy diagram that accounts for those changes. So right here in the middle is going to be where our starting materials are, and this is our alkyl halide and our nucleophile / base. And the z-axis coming out of the page towards us is going to be energy. We're not going to see energy differences from this view. We're just sort of looking down at the landscape. In the x direction, as we go from here to here, this is going to be leaving group leaves. So we could quantify that. This might be something like the carbon leaving group distance. And then on this axis, we're going to have, dang, I screwed up my axes, which I know is easy for me to fix, but not easy for you to fix. So, that's going to be the leaving group leaves. On the x-axis is going to be nucleophile attacks. And this could be like the carbon nucleophile distance. Okay? And over here at the bottom, we're going to have substitution products, which is going to have our leaving group has left, has gone, and our nucleophile has attacked. All right? So we've got two different ways to get from starting material to products. Well, actually three. Our mechanistic hypothesis one was that we go from here and we make the carbon nucleophile bond first and then the leaving group leaves. We ruled that one out because it involved a Texas carbon. The SN2 reaction pathway would be sort of directly across the middle here, because in the SN2 reaction, we make the carbon nucleophile bond at the same time as the carbon leaving group bond breaks. So that's our diagonal pathway. What's the SN1 pathway? Down and over, right? We break the bond between carbon and nucleophile first, or sorry, carbon and leaving group first. This point here is a carbocationic intermediate, and the leaving group has left, has gone, whatever that is, getting past participles mixed up. And then the nucleophile comes in on the second step. For the SN1 reaction, this first step is the slow one. This is the rate determining step. It's endothermic, meaning this corner of our diagram is higher in energy than this one. Okay? Now, we haven't really yet talked about what biases a reaction to go diagonal versus stepwise in terms of substitution. And we will. It all has to do with carbocation stability. What we have talked about, though, is the competition between getting substitution products and then getting elimination products. So over here, I'm going to put elimination products. So this would be like some alkene, and the leaving group has gone, and our nucleophile / base picked up a proton. There are, as before, we're going to use a different reaction coordinate. This direction is going to be beta proton is removed. Okay. the E2 reaction pathway is going to be going diagonal here. We remove the beta proton at the same time as the leaving group leaves. And you're going to see that there's a corresponding alternative pathway where the leaving group leaves first, and then we remove the beta proton. And this option is called E1. And the interesting thing is the first step for E1 and SN1 is exactly the same, leaving group leaves. And we're going to see that there's not any real selectivity between SN1 and E1 because this first step is the slow one. After that, it's fast, and the relative energy barriers to have nucleophile attacks a carbocation versus beta proton is removed about the same rate. So one conclusion from this is going to be that SN1 and E1 always compete. So when you draw SN1 products, you're going to always draw E1 products as well. Now, the way your text is written, they were going to hold that out in the back until the very end. They were going to teach you each of these mechanisms independently, and then they were going to say, oh, by the way, SN1 and E1 were competing the whole time. I'm trying to be upfront about that, and it's a little more complicated this way, but at least you won't be disappointed in the end, maybe? I don't know. Questions about how we've drawn things here? Yeah?
So the SN1 and E1, are they like the example that you did right at the end of the lecture on Wednesday about the iodide, like spraying them out?
Right. So what would we get? Iodide leaves, and we're in a situation where we can't do SN2, and this is not a good base, so we're not going to do E2. So all we can do is wait around for the leaving group to leave. We get a carbocation. Then what can happen to the carbocation? A nucleophile can attack the positively charged carbon, but we're going to use the same argument we used above for the alkyl halide. Some of the LUMO, which is mostly the beta, which is mostly the empty p orbital on that carbocation, some of the LUMO is going to spread out onto the adjacent carbon-hydrogen bonds by hyperconjugation. Right? So I'll just draw one of these. As we did before, though, we're going to have a situation like this where some of that empty orbital spreads out onto the beta proton. So your nucleophile slash base at this stage can do one of two things. You can attack here at the alpha carbon, or you can attack here at the beta proton. If you attack at the alpha carbon, you get a substitution product. At the beta carbon, you get the elimination product. And you're going to get both whenever you have a carbocation intermediate. Okay, we'll practice more on Monday. Have a good weekend.